to automatic MlMO for 6G. So this is Boya from University. Together with my colleague, Dr. Yunnan Zhang, also from University, we will deliver this tutorial. Okay, so the objective of this tutorial are multifolded. First, we would like to introduce a new paradigm to achieve automatic MlMO using a novel type of antenna array called Reconfigurable holographic surface, and it will have multiple applications in the areas of wireless communication and RF sensing. Second, we would like to understand how to optimize and analyze RHS-aided networks. From the perspective of communications, we aim to approach a higher data rate, and for the sensing applications, we desire a higher detection accuracy. Beside of this tutorial, we will also have a demonstration that is on the first floor tomorrow. That is the 13th demo named as RHS-enabled energy efficient millimeter wave automatic MlMO communication system, and you are very welcome to vote for our demo once you review it. Okay, so here's the outline for today's tutorial. First, we would like to show you a background on 6G communications and the KPI requirements, and then we will give you the holographic surface basics, that is, what is a holographic surface, why do we need it, and what challenges will be brought by this new type of metal surface. In the second part, we will deliver the content related to RHS-aided wireless communications, starting from the basic math and modeling. We will show 4 different case studies, from beamforming to application of satellite communication, and then codebook design, lastly, the channel estimation. For the second type of application, that is RHS-aided sensing, we will give you the radar and SLAM, also the recently quite hot topic, ICCC. And lastly, we will show the physical implementation and also the prototype developed by our lab. So now let's move to the background part. We know that we are standing at the crossing point of 5G, between 5G and 6G. And we know that wireless communication system towards 6G has its own KPIs, such as a higher peak data rate, a better energy efficiency that is 10 times compared to 5G, and also a high area traffic capacity. So how to achieve this? Recently, there's a type of there's a type of solution related to the term holographic. So here, before we move into more details, we would like to share with you three potential interpretations at different levels related to holographic communications. So in the higher level, holographic refers to the sci-fi applications you might see in those movies, that is, to achieve a fully immersive, real-time and three-dimensional experiences. However, to approach this goal, we actually explore it from two different aspects, that is the vertical bound and enabling techniques. For the vertical bound and the holographic MlMO, explores a continuous aperture packing infinite number of antennas, and researchers have did some work on the ultimate degree of freedom achieved by holographic MlMO. So that is from the aspect of vertical bound. But how to approach such a bound, then we move to the enabling technique, which is also the focus of our tutorial today. That is how to achieve a ultra-high spatial resolution via the extremely large-scale and densely packed antenna array. That is the way to achieve this ultimate degree of freedom in practice. So today our focus is how to approach such an extremely large-scale antenna array. So let's take a look at the traditional enabling antenna technologies. For example, the phase arrays. It works for both 4G and 5G. So at the bottom of this page, you may find a paradigm that's how phase array works with the whole communication system. So from the baseband module, the signals are sent to the RF module. And then by connecting with the RF chains, it will traverse phase-controlled beamforming. And from the structure of phase arrays, you may see that it has a lot of active components such as phase shifters, power dividers, and also power amplifiers. So that means for the phase arrays, when you have multiple RF chains, each RF chain connected to a path, or let's say connected to one power divider and to multiple antenna elements. However, such approach may have its own technical barrier for considering these current antenna technologies. For example, when we talk about phase arrays, it actually has a limited scale in commercial. That is, usually we have around the order of hundreds or smaller than 100 elements for this commercialized phase array. And also, it may suffer from a high energy consumption due to those complex feeding circuit network. It leads to an unacceptable cost due to those expensive active components such as phase shifters and power dividers and power amplifiers. Up against this background, it urged a new technology as to approach a large-scale, energy-efficient antenna solution. That is, we aim to have 3 different goals, which is large-scale, high frequency, and low cost. So how to achieve this? Then we move to a traditional antenna to see whether there are some new chances. That is the holographic antenna. So when we talk about holographic antenna, we need to start from a concept named hologram. So holographic antenna actually applies the principle of hologram. As you can see in the top left figure, a type of holographic antenna is actually an ultra-thin structure. It consists of numerous metallic patches that leads to a large scale at a quite low cost because the whole antenna bases on a PCB level manufacturing. Also, it has quite an ultra-low power consumption because there are no phase-shifting circuits and power dividers and power amplifiers within this holographic antenna. So this type of antenna array has already been applied to multiple military applications such as satellite communications and radar detections. Also, it has also been used in emergency communications due to its ultra-thin and light-weighted structure. So for the principle, we will talk about how it can achieve these benefits. So let's talk about the microwave hologram principle. So for the holographic antenna, it's actually a type of liquid wave antenna. The surface composes of numerous metallic patches, as we just mentioned, and there is a feed, as shown in the right-hand side figure, that the feed actually sends the transmit signal into the surface, and then the EM wave carried by the surface propagates along the surface. When it traverses each element, it leaks different energy towards the free space. So that's why it is a type of liquid wave antenna. So the key idea is like this. For this type of antenna, our aim is to generate a certain beam towards a certain direction. So the input is the transmit signal fed by this feed, which is also carried by the reference wave. And the output is to generate directional beam that is different. That is a certain EM radiation pattern of the objective wave. How to transform the input into the output? Then we use this specific placement of metallic patches on the surface. That is, we use these patches to generate a holographic pattern. So now we have three different concepts, right? As you can see, reference wave, holographic pattern, and objective wave. Then let's see how these three concepts interact with each other. So the working principle bases on these concepts and has two different steps. The first step is holographic pattern recording. That is, we use this metallic patch placement to record a holographic pattern that is bi-holo, as shown here. It depicts the interference between the reference wave and objective waves. So we have this. So we have this mathematical expression as shown here. And then for the second step, that is the holographic beamforming. So now we have a certain holographic pattern already recorded by this surface. And then in the second step, we input the reference wave via the feed. It will interfere with the already recorded holographic pattern. So in this way, we can then have something like this, right? As you can see, the reference wave is multiplied twice. So it becomes a real valued term. And then we have a complex valued objective wave here. That means the objective wave can be recovered by the phase and amplitude information within it. Okay, so that's the two steps of the working principle. However, when we talk about this traditional type of holographic antenna, it also has its own limitations. That is, once we have manufactured this holographic antenna, the placement of its metallic patches is fixed. That means one holographic antenna only has a fixed beam pattern. It is unable to support the mobile scenarios, which is what we do not want to see. Therefore, we actually extend this concept and solution into a new type of metal surface, which is reconfigurable holographic surface. In more detail, we apply the reconfigurable metal surface technique to the holographic antenna design, and then the holographic pattern can be reconfigured. In other words, we can generate different beams towards any directions. Okay, so when we talk, let's have a quick review of the metal surface technique. You may already be quite familiar with this. So a metal surface is a thin surface composed of sub-wavelength elements, and each metal surface element only has a quite low-cost active components that are pin diodes. So when the biased voltage on the pin diode is controlled, we can then have different EM responses. The benefits of metal surface are quite obvious, that we can generate directional beams, and also it exhibits the benefits of low cost and low energy consumption due to these quite simple diodes. So let's see, when we apply this metal surface technique into the traditional design of holographic antenna, what will happen? We have an RHS, that is reconfigurable holographic surface, which is also the main character, the main role of our tutorial today. So for its working principle, it is also quite simple. Let's see. So in the first step, as you can see from the right-hand side figure, there is a feed at the bottom or at the side of the whole surface. it is connected to an RF chain, and the feed inputs the reference wave, which transmits signals to the whole surface. And when the reference wave arrives at each RHS element, it interplays with the holographic pattern already recorded on the surface, and then radiates energy into the space. So in this way, the holographic pattern is actually recorded by the amplitude responses of these elements. And for each element, such amplitude response is dynamically controlled by diodes. In the third step, after traversing across the whole surface, the reference wave then turn into radiated signals in the free space. Since we have a large number of elements, so these waves radiated into the free space are superimposed to form directional beams, that is the objective wave. Okay. So you may wonder, so when we talk about that a new type of matter surface, what new constraint, or what's new? What's the news and what's the difference between this matter surface and other types? So we will give you a unique constraint that's brought by this matter surface, which is the leakage wave constraint. So as we can see in this figure, the RHS follows a series feeding mechanism. That means when the feed inputs the energy into the signal towards this surface, it actually propagates as water wave. So each RHS element is actually excited one by one. In this case, it makes a gradual attenuation of the reference wave during the propagation along the RHS, right? That is also familiar, which is the propagation loss. In this case, when you consider the radiated power, that means the sum of radiated power from all RHS elements is actually limited by the whole transmit power. Therefore, we have a new constraint to be considered when we talk about RHS, that is shown here. So eta here is the attenuation factor, and m here refers to the radiated power at each element. So since it is the amplitude response, and the square of amplitude represents power. Okay. So by summing up the whole the elements above the whole surface, it should be no larger than the total transmit power. So by observing this constraint, you may see that each element, actually adjacent elements on this surface, are actually coupled with each other. So that's the key point of this leakage power constraint. Okay, so let's make a quick comparison between the traditional phase array and RHS in terms of the transmission mechanism and the modeling. So for the RHS, the RF chain is always connected to the feeds. That is, there's no power divider, as you can see from these two figures. So the top figure refers to RHS. We can see that from these RF chains are directly connected to different feeds, and then the wave travels along the surface, such as a power wave, and then to the free space. Okay. So differently, the phase shift actually, these RF chains are connected to different power dividers, and then to multiple elements. So that's the difference in terms of the hardware. And in terms of the modeling, we can see that the key difference lies in these two equations. Okay. So for the digital beamformers, they are the same. They both obey the digital beamforming power constraint. But for the analog beamforming, the RHS should follow the leakage power constraint, which is we have already mentioned just now. But for the phased arrays, we know that the phased array always have the same amplitude response at each element. It only has different phase response at each element. So that's why the analog beamforming power allocation actually obeys an equal allocation principle. So that's the differences between them. Later, we will show that due to such a difference, we need to design the new beamforming mechanism for RHS. And now we know that in the past 5 years, race has been a quite popular concept. So here we give you a comparison between RHS and race. So actually they have a quite different physical structure. That is, the the R front end is directly integrated into the whole metal surface. But for race, the R front end is actually outside of the surface, as shown here. When you have some signal, for example, from the base station or from a source, it will be injected towards this surface and then be reflected. So there's a distance between the source and the surface. But for RHS, the source, which is also the feed here, it is directly integrated into the surface. So that's why RHS has an ultra thin structure, and it can be highly integrated with the transceiver. So in terms of the applications, RHS is quite suitable to be applied as transmit or receive antennas, but race is usually deployed as passive relays. So in this actually also RHS can be used for sensing and microwave imaging, but race is usually deployed at the cell edge for coverage extension. Okay. So now let's take a look at two typical applications. That is, the first one is how to apply it in the area of wireless communications. So since we know that this such a type of RHS can have a large scale and ultra thin deployment, so we can use it to enhance the spectral efficiency, especially to approach the ultra massive MlMO for 6G. In this way, it provides a ultra high spatial diversity gain. And secondly, since RHS has no active amplifiers and complex phase shifting circuits, it can improve the energy efficiency of the whole system quite significantly. Okay. And for the second type of applications, that is wireless sensing. So since this is a type of antenna array, it is natural that it can serve as the antenna in the radar system. So due to its superior beam steering capability, we can enhance the detection accuracy, and also we can reduce the complexity and cost of the whole radar system based on RHS. Also, since we have radar, we have communication, we can then move to the RHS-aided ISAC. That is to increase the integration density of ISAC system due to the low profile. That means it is ultra thin of the RHS. So here's the some key takeaways to be covered by this tutorial. So first, we will show you that RHS actually changes the beamforming design compared to both rays and phased arrays. We will talk about its unique real valued amplitude control constrained by this unique leakage power limitation. And also we will show you a low complexity holographic beamformer superposition while the holographic pattern superimposed. And the second, RHS actually provides an implementation manner to achieve the concept of holographic MlMO. That is because RHS actually exhibits a quite dense element spacing, far smaller than half wavelength. And due to the feature of amplitude control, we can get a scale-changeable RHS array to generate flat and wide beams that is suitable for beam training. And also the channel estimation for RHS are also different because we need to generate an over-complete sampling matrix, which is different from the traditional phased arrays. And the last takeaway is related to the RHS sensing, that we, after our analysis, we found that the two-dimensional RHS radar shows a superior detection and range estimation accuracy at high frequencies compared to the two-dimensional race case. So that's the basic background of our tutorial today. Now let's move to the mathematical and modeling part, and also some different case studies that how we can do some research around this RHS communication. So let's have a quick recall of the working principle of holographic antenna. We mentioned that we have three different concepts. That is the reference wave, the objective wave, and the holographic pattern, right? We have two steps to perform the holographic beamforming. The first one is to record the holographic pattern via these metallic patches, which is to use these patches to generate a holographic pattern, that is the interference between reference wave and the objective wave. Okay. And then the second step is to use this holographic pattern to interfere again with the input reference wave. The reference wave carries our transmit signal. And in this, then in this case, we can recover the objective wave. So how to achieve this? We will show you some detailed mathematical equations to help you understand the whole process. So for the first step, that is to record the holographic pattern. So we put down the specific form of reference wave, objective wave, and the holographic pattern. So as you can see, it takes a form of the exponential formula. Then the Ks here refers to the propagation vector of the reference wave, and the R vector here actually is the distance vector from the kth feed to each element. And then we have this objective wave. So for the objective wave, the wave number k becomes a propagation vector in the free space, and the also theta 0 and phi 0 refers to the position of theta 0 phi 0 refers to the desired direction. That's our goal. That is which is our beam to be generated. So in this case, we can simply put down the holographic pattern as the multiplying the reference wave and objective wave. So at the bottom, we show you the specific mathematical form of those propagation vectors, as well as the ID of each RHS element. Okay, so here's some further formulas for you for reference. And then in the for the first step, we also would like to know how can we record such a holographic pattern just using these metallics, right? Metallic patches, right? That seems quite unnatural. Actually, the fact is, we record the real part information of the holographic pattern using the amplitude response of each element, and such amplitude response can be adjusted by the embedded diodes. So we show that m here. So the small m here refers to the amplitude response of one element, and we can see that it takes a form of the real part of the holographic pattern and regulated with between 1 and 0. And the key idea is that when the phase shift of the reference wave at an element is different from that of the objective wave, the element is detuned and radiates little energy into the free space. That means infers the small amplitude. Otherwise, the element is tuned to radiate much energy, which refers to the large amplitude. So that's why we use the amplitude control to record this holographic pattern. So here's the detailed, so here's the mathematical details of the holographic beamformer. That is also our second step. So we follow the traditional formula as y equals HMS plus n. N is the noise, and H refers to the channel response. And the holographic beamformer we recorded or we denote as an uppercase M. So to generate a beam towards a certain direction, for example, theta 050, M is also actually formed by this. So as we can see that the small m here refers to the holographic pattern which we just mentioned earlier, and the second term, that is the blue circle one, refers to the refers to the reference wave. For the reference wave part, we can see it has multiple terms, right? So let's take a look at them one by one. So eta refers to the ratio of the power accepted by one RHS element to the total transmit power, and the vector r refers to the distance vector from the kth feed to the NYNZ's RHS element. Okay, so that's a distance vector on the surface. Okay. And then for the exponential part, the first one refers to the propagation loss of the reference wave on the surface. We just mentioned that the reference wave actually propagates like a water wave on the surface, right? So naturally, it has a propagation loss. And the last term, which is also an exponential term, that refers to the phase of the reference wave. So as we just mentioned, the reference wave propagates along the surface. So naturally, the phase of this reference wave varies along its propagation on the surface. So that's why there's a term like this. You may wonder that how can we deal with this, since it seems quite complicated. But the truth is, you only need to deal with the m term. Okay, so only the small m here, which is the amplitude response, is unknown. This is the variable that we aim to optimize. But for these terms, they are actually all unknown parameters. We only consider them when we modeling them, but we do not need to optimize them. Okay. So here's a question naturally arises. So just now I mentioned we have this holographic pattern, we have this holographic beamformer, and our goal is to generate a directional beam towards any direction we desire. But how? Why such a beamformer can generate these beams? So now let me give you the answers. Suppose we use the method that we just mentioned to generate a holographic beamformer M already. We put it here. So at the first line, which is the formula that we just mentioned, and then we transform the cosine part into the sum of these two exponential terms. And by reformulating the whole formula, we then have this. So let's take a look at these terms. The green one actually is the objective wave. Okay, you can see that from the exponential term, it exactly takes the form of an objective wave. And for the second part, these are some neglectable side lobe item which we define as C. So here, let's show how it looks in the EM pattern. You can see that the objective wave is already recovered. That is the main lobe. And this neglectable side lobe term can be seen here. So that's why this equation actually works. That by using such a holographic beamformer, we actually do generate one beam. So to help you understand better, we will also share a simple example. That is, suppose for an RHS with one feed and only two RHS elements. Okay, so it only has two elements, and then in this case, the holographic beamformer is actually a vector. The vector only has two elements. Okay. In this case, we can directly put down the specific form of M, that is the first term and the second term. Okay. And after we send the signal X to the holographic surface, and the signals can then be given like this. So that is M times X, right? So we can see that this term actually refers to the objective wave towards 6050, and this is also the same. But why there is a R1 and R2? That is because we have one feed and two RHS elements. Okay? So we have two distance vectors on the whole surface. Okay. So in this way, the signal emitted from each element actually is towards the same objective direction, 6050. So that's the way how we can generate beams towards these directions. Okay. So after these mathematical details, let's take a look what new challenges are brought by the RHS compared to the traditional phased arrays. We can see that there are two distinct differences between them. The first one is the transmission form actually changes from parallel transmission to serial transmission. That means for the phased arrays, the signals actually are simultaneously fed into each element. Okay, that is also the same with rays. But for RHS, we just mentioned the way the signal propagates as water wave along the surface, element by element. So it's called serial transmission. The signals propagate element by element. Okay, and then for the second obvious difference is it's for phased array. We have the phase control, right? But for RHS, we focus more on amplitude control. That in this way, we can actually tune or detune each RHS element. So the amplitude response of each element can be 0 and 1. And when the amplitude response is set as 0, this element actually does not work. In other words, we can have a scale changeable antenna array via the amplitude control. Based on these two different features, we need some new transmission models and the beamforming technique. That means we need to build a new transmit model by introducing this the leakage power constraint as well as the serial transmission type. In this way, we need the low complexity holographic beamforming to generate both flat and narrow beams. And for the second feature, that is the amplitude control, we give you the scale changeable array. So the traditional phase control beamforming does not apply anymore. In this case, we also find that this power control is coupled with the amplitude control based on holographic beamforming. That will lead to some new, that will require some new resource allocation schemes. Based on these mathematical details and the differences and new challenge brought by RHS, now let's move to the case study part. So first, we would like to show you how to use these holographic beamforming schemes to support multiple users. Consider a downlink RHS-aided multi-user communication system. So So we have one base station equipped with an RHS transmitting to Q users, and each user is equipped with a single antenna. The RHS has Q feed. So Q feed means it is connected to Q RF chains, and it has N radiation elements. So the key questions are how to model the signal propagation on the surface and how to generate multiple beams in this RHS-enabled holographic beamform. So here let's take a look at the RHS-aided hybrid beamforming framework. So for the hybrid beamforming, we actually have two parts. The first one is at the base station, we have the traditional digital beamforming, okay? So this beamformer is denoted by the matrix V. Its size is K times Q, okay? And after the digital beamformer, it is directly connected to K different RF chains, and each RF chain is connected to one feed of the RHS surface, and then the signal propagates along the surface and then to the free space. So in this case, we denote the holographic beamformer as M at the RHS. In other words, the holographic beamforming actually enables the function of traditional analog beamforming. We have this traditional equation as YQ, that is the received signal of user Q. It equals HQ times MVS plus naught. So based on this y equals HMVS plus n type, let's take a look at the only new thing in this equation, that is the holographic beamformer M. So M is a complex matrix with the size of n times k, okay? And each element of matrix M takes a form like this. You might be a little familiar already with such a form that we just mentioned. The M here refers to the radiation amplitude response. Okay, so it takes value from between 0 and 1. And the amplitude response of each element is actually controlled via the diode. So the holographic pattern of the RHS is actually recorded via these amplitude responses of all elements. That is the set. That is a collective set of all these MN. So this part is what we aim to optimize. It is unknown. And for all the other parts, they are all known parameters. You don't need to worry about them because you can directly put down these once you have an RHS surface and once you know which direction you aim to transmit. Okay, so R here is a distance vector, and the first exponential term is the propagation loss, and the second one refers to the phase information of the reference plane. And what's more, we would like to emphasize again that we have a unique power constraint brought by series feeding. So now you may wonder, it seems quite simple, but later when you move to the optimization part, you may realize that this one actually brings some difference when we consider the optimization and algorithm design. Okay, so it refers to the sum of radiation power from all RHS elements should be limited by the whole transmit power. Okay, so when they put this liquid power constraint into the whole system, again, it's obvious that this part are the main difference between the traditional beamforming and the holographic beamforming, right? We have this unique constant. And for the phased array, let me repeat again that phased array explores the parallel transmission, which means it is equally divided power on these elements. So one thing you might wonder that you may also have power control when you consider the phased array enabled beamforming. That is true because we also have this power allocation at RHS. But when I mentioned the equally divided power, I mean the amplitude response of each element on the phased arrays. So for the problem formulation, we can directly put down the achievable range of each user. So this step is quite classic and traditional, that we have 1 plus SINR. So this HQ refers to the channel matrix between RHS and user K, and we have this sigma, prescribed sigma as the noise power, and this part is actually the interference term. So then we can have the sum rate maximization problem as the sum data rates of all users. And in this case, let's take a look at that where the leakage power constraint takes place. That is in the constraint part. In that way, it means we actually have an actual constraint, but the traditional constraint, which is the power constraint, also exists. And what's more, we need to mention that the amplitude response takes values between 0 and 1. That is the regulated result. Okay. So by observing this power constraint, we find it is different from the traditional water filling power constraint, because it takes a quadratic form that is different from the traditional linear form of power constraint, and this will bring us some new thoughts and new challenge when we are designing the algorithms. Okay, so to simplify this problem, we can directly decompose it into two sub-problems. That is the digital beamformer and the holographic beamformer. And we use so we have two different methods to solve this problem. The first one would be quite direct and also high complexity, but it may give you a near optimal solution. That is, you directly use an iterative algorithm to solve the digital beamformer and the holographic beamformers iteratively. So we have nothing to say about the digital beamforming part. That is quite classic and traditional. But for the holographic beamforming part, we can use a fractional programming technique to eliminate the non-convex ratio, that is the SINR part. And then we recast the data rate of each user into the maxima of a concave function. In this way, we can solve this concave function-based maximization problem. Okay. So here's some simulation results for this first method. You can see that from the left-hand side figure, the sum rate grows rapidly with a small size of RHS and then gradually flatten, which is not news for you because that happens almost related to all types of antennas. But what's new is the second figure. We actually we introduce a parameter C, which is defined as the cost ratio of the phased arrays TR module to the metamaterial radiation element. Okay, so since we know that the cost of RHS is usually much smaller than the phased array, so let's take a look at the result on hardware cost. We can see that at the when we reach the same sum rate result, the cost of RHS is actually much lower than the phased array counterpart. So we actually achieve a higher cost efficiency. Okay, so the first method is quite straightforward, but you might not be that excited about it. So let's move to the second method, which is a unique part of the holographic beamforming. And for this second method, let's see. So why do we need to? Why do we move to the second method? That is because for the first method, when we directly solve the holographic beamforming, the number of variables for the holographic beamformer optimization is quite large. it actually equals the number of the RHS element. That means, suppose we have a large antenna scale, maybe 1,000 elements. Then we need to solve these 1,000 variables. That leads to quite a high complexity, especially for ultra-massive MlMO. So in this case, we do not want such a scaled-up complexity with the growing number of RHS elements. So that's why we move to the second method. We want to use the unique feature of holographic pattern superposition. So we just mentioned that the holographic beamforming takes the form in an amplitude control, right? And we know that the amplitude, the squared amplitude is power, and this real-valued vector actually can be summed up, right? Energy can be summed up, but phase cannot. Therefore, that means the holographic pattern can actually be directly superposed. On this basis, we propose a low-complexity beamforming scheme based on a weighted sum of different single-beam holographic patterns to directly generate the multi-lobe beams in a quite lightweight manner. Okay. So here's the key idea. So as you can see from this figure, so on the left side we have two different holographic patterns, right? So the red squared implies that the element is tuned and it radiates energy in the free space. Okay, so these two holographic patterns aims to achieve single beams. And each holographic pattern represents a specific RHS element amplitude configuration that corresponds to an EM field radiation distribution. And then, suppose we want to generate two different beams towards different directions. That happens every day in the mobile communication. We can directly sum up these two patterns into a superposed one. Okay. Then it directly generates multiple beams. Okay. So that's our design idea, and then we will achieve this. Okay. So let's see mathematically why it stands. So to start with, let's recall how we generate a single beam holographic pattern. We directly show you this proposition 1, that is, to generate a single beam, we can put down the radiation amplitude solution in a closed form. Okay, so previously we've already shown you some mathematical proof that why it can generate a single beam. Okay, and then and for the intuitive interpretation, we also shown here that is due to the phase shift difference between the objective wave and the reference wave, which is the principle and guideline why we tune or detune one element or not. And given this given multiple single beam holographic patterns, if suppose we want to generate multiple beams, suppose a K-beam holographic pattern, it can be directly obtained. That is, we found that the amplitude of an element is a real number. It reflects the radiated energy, right? So each holographic pattern can be recorded via the amplitude distribution of the RHS. Such additivity also holds for the holographic patterns. So we can directly use a weighted sum of multiple single beam holographic patterns to generate a complicated K-beam one. So in this case, as you can see at the bottom, suppose we have two. So these are two single beam holographic pattern, and then we use the weighted sum. As you can see here, we then get a complex one. And mathematically, we can use this equation to show the superposition happened here, that we introduce a weighting factor A. A refers to the weighting factor of the K beam, and then by summing up all the predefined single beam holographic pattern, we have a compound one. Okay. And also, do not forget that the weighted sum, that the weighting factor also satisfy this sum one constraint. So in this way, let's reformulate the previous holographic beamforming problem in a simpler way. So previously here, we need to directly optimize the amplitude control of every RHS element, Mn. But now we do not need to optimize Mn. We only need to optimize A here, and this M is known, right? It refers to the single beam amplitude control configuration. So the small m here is known, and the A is unknown. So we can then reformulate the holographic beamforming problem like this. The unknown variables now changes to AQK, and its sum equals 1. In this way, the complexity of a multi-beam holographic beamforming is only proportional to the number of users k, right? For k users, we need to generate k different beams, so the number of weighting factors is k. And also, unlike the traditional power domain water filling, you may find that we need to deal with the projected form of AQK, which is also the new challenge brought by such a holographic beamforming problem. So I wouldn't dive into these mechanical details. You may refer to our technical papers. So these two slides just show you that how to solve this multi-beam holographic pattern problem. So we actually use zero forcing digital beamforming as an example, and then derive the upper bound of the sum rate. And based on the upper bound, we can get the closed form, basically the closed form or solution of the weighting factors AK. Okay, so it's shown here. We can optimize it by using the Lagrangian dual form and directly get this. Okay, so lastly, in this first case study, let's take a look at the comparison between the RHS and phased array enabled multi-lobe beamforming. So we introduce the ratio of the sum to the hardware cost as the cost efficiency, and then we already know that the cost ratio of phased array to the RHS of the same number of elements is actually around 2 to 10. Okay. And so we compared these two different types of antenna arrays. We find that the superiority of the holographic-based scheme in cost savings becomes clearer with the number of elements n and the beam ratio beta. So just now we mentioned basic work that how can we generate multiple beams based on the holographic beamforming and to support multiple users. So now let's move to an extensive work that how such holographic servers can support satellite communications. So the motivations are so for traditional antennas used in satellite communications, they are basically dish antennas or phased arrays. They either require quite heavy mechanical components or costly phase shifters. But new satellite communications now calls for novel, cost-efficient antenna technologies with lightweight structure to overcome the limitation of traditional antennas. So in this work, we actually proposed an RHS-aided multi-satellite communication scheme by jointly considering the mobility of LEO satellites and the RHS-based multiple access scheme optimization. And we also evaluate the robustness of the proposed algorithm since we are facing the satellite communications, right? So we aim to guarantee that the tracking errors of the satellite positions can hardly influence the maximum sum rate. So let's take a quick look at the system module. You may find this model also quite familiar, that we consider one user terminal that is equipped with an RHS. It is on the ground. Okay, so such a user terminal uploads terrestrial users' data streams to the satellite for uploading. And then for each RHS, we consider it has L feeds and multiple radiation elements. Each satellite also have K-receive antennas at the same altitude h, and the position of each satellite is known to us. The distance vector can be directly put down based on some geometry information. So when we consider the multi-satellite communication, we show you a quite simple paradigm that consists of two parts, which are the new satellite tracking scheme and the RHS-aided multiple access scheme. We divide the time of communication into T time slots, and during each of which the position of each satellite is considered as unchanged. In the first two time slots, the user terminal transmits the signals to the satellite via the RHS-based holographic beamforming based on the initial satellite positioning information. And in each of the following time slots, the user terminal then tracks the position of the LEO satellites based on the temporary variation law of the satellite's positions, and then updates the holographic beamforming scheme accordingly. So let's take a quick look at the LEO satellite tracking scheme. So we track the satellite based on the temporal variation law. That means since the satellite are always scheduled in advance. So when we know when we know in advance the its positions of the first two time slots, we can always infer the next move, the next several moves of the satellite. In this way, we can avoid frequent satellite positioning. And for the second part, that is also a sum rate maximization problem. Once you already have an inference on the satellite's positions, you can try to maximize the weighting factor A, that is the amplitude ratio for the beam pointing to different satellites from different feeds of the RHS. And then we can sum up the data rates of all satellites by all that they receive signals. So here there's a W that refers to the receive combiner as the satellite, and HQ again refers to the channel matrix. So we also have a holographic beamformer that is denoted by the matrix M. So here we use the holographic pattern superposition. In this way, we do not need to directly solve the small m here. We only solve the small a here, and then we can directly get the holographic pattern by superposing. Okay. And these two exponential terms, they are all known to us, but always remember we cannot ignore these two terms, despite their known vectors. So let's take the algorithm design and then we'll directly move to the simulation results. We find that we evaluate the robustness of the proposed sum rate maximization algorithm against the satellite tracking errors. So the tracking errors of the satellite angles are set as large as 10 degrees, and the tracking errors of their altitudes is set as large as 10 kilometers. So those are simulation setups. Then our evaluation revealed that the proposed sum rate maximization algorithm is actually robust against these two types of errors, as you can see. So which is good news. Okay. So just now we showed you two case studies based on a strong assumption. That is, the channel information is known, right? The channel matrix H is known in the previous two case studies. But we are also aware that in practice, when we consider the ultra-massive MlMO, the channel matrix can be quite complicated and non-trivial to be measured. So in this case, it is necessary to consider when the CI side, when the channel state information is not accurate, maybe we can use the codebook design and beam training to avoid this CI side information acquisition and again get a high spectrum efficiency. So this is the key idea of our third case study, that is the theoretical codebook design using a scale-changeable RHS in near-far field communications. So before we start the details, so why do I include the near-far field communication in this work? It's because we are considering an ultra-massive MlMO. We are talking about a large-scale RHS array. So that's what. In this case, the range of the near field region actually expands, right? So users may randomly be distributed in both near field and far field. Okay, so that's the key reason why the background includes near field and far field. And let's take a look at some existing problems when we consider the codebook design and beam training. So usually when we talk about the codebook design, we consider some multi-beam coverage code words. That means a code word refers to a multi-load beam. It can cover different areas in the free space. So this is called the multi-coverage code word. But it is not that easy to design such code words. This is because the beam coverage usually depends on the array aperture, and code words with different beam coverage are actually hard to be designed in scale-fixed phased arrays. So here we show two existing methods to design multi-beams. So this one is, you can find it quite frequently in the existing literature, that if you want to get a multi-beam code word, you use multiple single beam code word to generate a multi-beam. But the drawback of this method is that you can see it is not, the power density is not distributed evenly, right? You can see there are quite severe, quite severe propagation loss here. That is the fluctuations or even collapse in the beam pattern there. So this is not what we desire. And for the second existing method, one may need to add some extra hardware. So you may see some true time delay when you search the existing literature. But that works. Okay, that works when you generate the multi-beam code words, but it requires extra switching circuits. So that means, so what if we do not want to add extra hardware, but we also want to have a flat multi-beam code word? Okay. So now let's take a look at the solution related to holographic surface. We just mentioned that the holographic surface has a unique feature of amplitude control, right? The element with an amplitude of 0 essentially simulates the effect of being turned off. It is feasible to configure an equivalent RHS array by activating certain elements without additional switches and control mechanism. So the key idea is that for such a type of RHS, we can directly change its scale by turning on and off these elements. But that is not the case for traditional phase arrays, because for phase arrays, even if you can shift your phase shift from 0 degree to 180 degrees, all elements still work. They are not turned off. And we also know that the beam width is directly related to the scale of the antenna array. So by having this turn on and off feature of RHS, we can directly have a scale changeable antenna array. And by using this changeable scale, we can generate different beams of different widths. Okay, so that's the key idea. So using this observation, we can see that when we generate the RHS with single beams, it has a flat and wide coverage. So that's a benefit. And using this key idea, we can then design a theoretical code book. It has multiple layers. The upper layer code words can support the angular search, while the bottom layer code words can complete the distance search. That can be applicable to both near field and far field search of different potential users. And the design of our code book only requires 1-bit amplitude control, which largely simplifies our design and the hardware burden. And later, based on such a code book design, let's see the upper layer code words. They can support the angular search, so they have the same distance information. And for the bottom layer, we can see that it directly tells different distance between different points. And the overhead of the beam training based on such a code book is logarithmic level of the antenna number as we analyzed here. So let's take a quick look at the simulation results. So we compare this RHS-enabled near-far field codebook design and beam training scheme with the traditional phased array-based scheme. We can see that RHS can achieve a higher data rate and beam training accuracy, since the RHS obtains higher transmit power given the same input power. And also the proposed scheme approaches the upper bound achieved by the exhaustive search and significantly reduced overhead. So after these 3 case studies, we've already considered 2 typical cases, which is when we know the channel state information perfectly, we can use the holographic beamforming, right, based on the holographic pattern superposition. And when the CSI is unknown, we can also use the scale changeable RHS to generate the theoretical code book and then beam training for both near field and far field users. And now let's consider some theoretical analysis. So just now we mentioned that RHS is based on amplitude control. The only active components are diodes. But when we talk about diodes, it is actually a discrete hardware, right? It has different quantization levels. So a question naturally arises is that how many context bits do we need to achieve the RHS-aided wireless communication? Okay, so the motivation is, I already mentioned the motivation is we aim to review the relation between the radiation amplitude context bits and the sum rate. And to achieve this, we first discuss the relation between the sum rate with continuous amplitude values and that with the discrete levels. Okay, and then we derive the closed form expressions of the minimum context bits to reach the sum rate threshold. Okay, so the system model is quite simple, and as usual, again we consider a dominant RHS-aided multi-user communication system, and the base station is equipped with an RHS array. We perform the RHS-aided hybrid beamforming. That is, the RHS perform the holographic beamforming resembling the analog beamforming function. Okay, and then for the analysis part. So first, let's formulate the context bit minimization problem. That is, how many bits at least is required if we want to achieve such a performance threshold. Let me, so the R sum hat refers to the sum rate with discrete amplitude, and the R sum here is the upper bound. That's the sum rate with the continuous amplitude. So when you put down this problem, you will find that it is quite hard to achieve a closed form solution for Q, because the R sum hat does not have an explicit function of Q. So in this case, we directly use a lower bound of R sum hat to replace it. So we will give you this formula as the lower bound. We find that it increases as the contrast bit Q grows. And then we can use this lower bound to achieve the closed form expression of the minimum contrast bits. In the single user scenario, we have a very straightforward lemma that one bit is already enough when the RHS says it's sufficiently large. So that's also it's also aligned with your intuition. So the simulation results show that basically 2 bits are already sufficient to approximate the sum rate with the continuous amplitude case in the multi-user case, and 1 bit is already enough in the single user case. So that also serves as a guideline when we design the hardware to implement RHS. Okay, so for the last case study of the RHS-aided communication part, let's talk about a quite practical issue, that is the channel estimation. So this is actually what we cannot escape from when we consider ultramassive MlMO. If you have such a large antenna array, you have quite a lot of channels to estimate. Of course, we can use we can use codebook design and beam training. But what will happen if you aim to explore the specific the specific features of channel distribution? Okay. So let's talk about the near-far field channel estimation with the densely packed RHS. So here's the motivation. We just mentioned that RHS have 2 different features. The first one is it can be built into a quite large scale, right? So in this case, we need to solve the we need to confront the hybrid near-far field channel, because the scatters and users may randomly be distributed in both near and far fields. And the second one is RHS actually actually has a quite dense antenna spacing. You may be familiar with the concept of HMlMO, right? And the key idea of HMlMO actually mentioned that the antenna spacing is quite small, that it is a constant continuous aperture. This is actually the same for RHS. When we design this antenna array, we found that the antenna spacing is usually far smaller than half wavelength. Okay. So the contribution of this work is that we propose a compressive sensing-based channel estimation algorithm so that the far field parts and near field parts are decoupled and estimated accurately. And also, we propose an adjustable angle sampling method for the RHS-enabled densely packed arrays to achieve HMlMO. Let's take a quick look at the system model. For the channel model, we use we use a collection of both near field paths and far field paths. So here is a quite simple illustration of what is near field and what is far field, right? When you consider near field, it resembles more severe waves, and for far field, it resembles planar waves. And for such an RHS-enabled transmission, there are 2 challenges of the channel estimation. First one is brought by the numerous antenna elements. Therefore, the channel coefficients may outnumber the pilot signals, such that conventional methods might not work well. And for second case is that the hybrid near-far field efficient leads to, that is, the coupling of the power of near and far field paths, which are quite difficult to be separated at each path. So the solution is to introduce a hybrid field compressive sensing. We decouple these parts and reduce the number of parameters to be estimated. So previously, the number of unknown parameters are proportional to the number of antenna elements, n. But now, when we turn to the number of paths, we only need to estimate 3 L near plus 2 L far. So L near refers to the near field, L far refers to the far field path. And 3 times, 3 here refers to the angle, distance, and the channel gain. Also, this 2 refers to the channel gain and the angle information. So when we perform the channel estimation, the first step is quite general, that we use a joint angular and polar domain transform design. This is to decouple the parts with a transform to utilize the channel sparsity. So here we construct a sampling matrix as shown here. It consists of the spatial domain channel and both the angular polar domain channels. Okay, so here I will show you some simple illustrations that we sample this whole space with far field steering vectors A theta and the near field steering that is B theta R. So when we consider the sampling matrix, here are some interesting phenomena. So for the conventional angle sampling, we directed the number of sampled angles equals the dimension of the space where HD, that is the channel, belongs. So usually people will apply the orthogonality between the steering vectors. So this is the main principle when people generate these steering vectors for sampling. But when we consider the RHS, as we just mentioned, the element spacing is quite small. So that's what's so there's some magic here. You can see that if you still use these orthogonal sampling vectors, we found that the angle resolution may be reduced. So as you can see, when D reduces by observing these equations, so M also reduces. In this way, the absolute value will be increased. That means the angle resolution collapses. So that's what we do not want to have. So to solve this problem, we turn to an adjustable angle sampling. That is, we try to relax the orthogonal constraint between these steering vectors. In other words, we increase the number of sampled angles as shown here. So previously, when we talk about an orthogonal samples, so the A times A should equal 0. But now we relax them and only require them to be smaller than mu here. So in this way, let's take a look at the resolution part. We can see that the resolution for angle separation is directly enhanced. Okay. So in this way, it's effective for compressive sensing that the channel sparsity exists, and also we can achieve a refined sampling, which is able to separate paths with close direction. And also, we increase the number of sampled angles. So the drawback here, that is the cost of this method, is we have a higher computational complexity. And now let's move to a second feature of the RHS, the large-scale RHS-aided channel estimation, that we may have a hybrid field power diffusion effect in the joint angular domain, angular polar domain. We find that when we transform the whole channel into this joint domain, there is a power diffusion effect. That means the near field parts in the transformed domain actually is expanded to the far field range. In this case, one may not be clear that which part is from near field and which part is from far field. There are multiple fake path to be estimated, which is not what we desire. So in this case, we propose a power diffusion aware OPM algorithm. It is actually a gradient-based algorithm that it estimates the largest magnitude in the joint domain in each iteration, and by iteratively estimate the power diffusion range of the highest path, we can directly eliminate the power diffusion effect in the gravity signals. So lastly, let's take a look at the simulation results for different SNRs. The proposed PD OMP channel estimation expects a higher estimation accuracy than the traditional MMSE and other baseline hybrid field algorithms. And from the second figure, we can find that by having such a densely packed RHS antenna array, we actually can have a freedom of adjustable antenna sampling, which leads to a trade-off between the estimation accuracy and the computational complexity. And then, but in this case, the estimation accuracy is saturated when the number of sampled angle M increases. So that works as a guideline that basically we can have an optimal number of sample angles M. Okay, so now we have just traversed the whole RHS-aided wireless communication part with all these four case studies. So maybe we can have a break. Okay, so we will be back in 30 minutes. And if you have any questions, please feel free to contact us during the break or eventually when the whole tutorial ends.